if you have a sum of two functions in the integrand, not just one function but two, then by the definition again, this would be the limit as n approaches infinity, summation of the sum, right? Oops. Plus 1 to n. Then you have the sum of these two, so f of x plus g of x, right? It's all one sum function. Oops. I need the sampling point expression in here, so xi star and xi star. So there's our function with its particular sampling to get the heights of the rectangles. And then on the outside we still have delta x. I'm just going to leave as delta x this time. I'm not trying to manipulate that part of it to illustrate this. But we know that a summation distributes in a sense across a sum. But so does a limit, as long as the limit exists. So both of these operators can now distribute across the sum of these two and apply themselves directly to f and g separately, and delta x will follow with each one because it's a multiply here. So we should have the limit as n approaches infinity of the sum of f of xi star, right, that sampling point in there, times delta x plus limit as n goes to infinity of the sum of g xi star times delta x when it goes from 1 to n. But each of these is their own separate definition of integral. So therefore this is nothing other than the integral from a to b of f plus the integral from a to b of g. And therefore, because the integral is defined in terms of a summation and a limit, and they both have the property of distribution over a sum, therefore the integral itself has that property. So now we see that if you have a sum within the integrand, that's equivalent to distributing the integral across both of those functions, evaluating the summation secondarily. Okay, so it has a distributive property. And that goes for negations as well. The whole problem would be the whole expression would be the same here. You put a negative in here, it would be a negative, negative, and negative. So with the sum or difference, it doesn't matter. The integral has a sum difference property. Just like limits, just like derivatives, and just like summations. All right. Another important property, if you have the integral of a constant times a function, you should be able to guess where this is going by now. A to b. So by definition, limit again. C f of xi star delta x. Again, leave delta x. I'm not trying to manipulate that. But we know that the summation symbol sigma has the ability to move constants, multiplicative constants to the outside, but the limit has the same property as well. Therefore, c can move outside of both of these due to the way that the integral is defined. So I have c outside both of them function, which depends on I, is trapped inside the summation. So xi star is still there, and delta x. But this is, of course, just the definition of integral again, with c on the outside. So a to b function dx. So we have a constant multiple rule for integrals, just like for derivatives, summations, and limits. Okay. So that's two important properties All right, the sum difference property and the constant multiple property that it shares with derivatives, so that should be easy to remember.